Our next speaker is growing, living human bone for skeletal reconstruction. She is the CEO and co-founder of EpiBone, and she studies the new frontier of biotech. Artificial hearts, homes, textiles, video games made of cells. Foreign policy named her one of the 100 leading global thinkers of the new industrial revolution. Nina Tandon.
Good morning. Hi. Are we enjoying the conference? Yes. All right, now I know it's maybe a risky time to do this, but as we settle down and get started, I wanted to invite everyone to do something a little bit non-traditional. And close your eyes. Close your eyes for a moment and imagine a world where we no longer have our energy issues because we're converting energy at a rate not only better than the sun, but 10,000 times more efficiently than the sun. Where we don't have an infrastructure problem because broken bridges can repair themselves. And our devices don't have an electricity problem because they're like a little pet, and you can just feed them a little bit of sugar, and they can recharge themselves because batteries are alive. Okay, you can open your eyes now. That sounds a little bit like science fiction, right? And in some ways it is, because we don't have these technologies in our built environment. But what I'd like to start off with is by saying we actually do live in that world. These are mitochondria. They currently, gram per gram, convert energy at a rate 10,000 times more efficiently than our closest star, the sun. These are osteocytes. Anyone know what these are? Any biologists? They build our bones every day while our bones are a calcium reservoir. So every time our muscles need some calcium, they steal them from our bones, and at night, these cells put it back where they're supposed to be. Our bones are like bridges that repair themselves every day. And just that exercise of closing our eyes and imagining entails the use of millions of neurons that power everything, that are powered by electricity. And that same bioelectricity powers everything from our heartbeats to our thoughts. Throughout most of history, we haven't really harnessed this power directly, except maybe through agriculture. So these are grapes. And at the molecular level, we've also harnessed this in the microbial level with what's called brewer's yeast. This is how we get all those amazing Belgian ales. In my work, I'm an electrical engineer. I first got interested in this because I was interested in the electrical currents that flow in the human body during embryonic development and wound healing. And this is an example of some cardiac tissue. Our largest bioelectrical organ is our heart. It releases electrical pulses with every heartbeat that are about 1,000 times stronger than the brain. And I was studying how we could get stem cells to become heart tissue by coaxing them with these electrical signals. So this heart tissue is actually beating in time with a circuit that I had built with my own hands. And it's about a 10-year-old video, and it never really gets old for me to look at that with a little bit of wonder at how our hearts are beating all the time. At our company, EpiBone, we use stem cells to grow living skeletal replacements. So this is an example, this picture here, of mesenchymal stem cells. These are stem cells derived from adipose tissue. That's a polite way of saying fat tissue. And after about 3 weeks, they grow in these beautiful swirling patterns that are almost evocative of a Van Gogh painting. And they're purple because they're marked for an early marker of bone development called alkaline phosphatase. And they're beautiful to look at. at least for me. And why do we do this? Okay, so at EpiBone, we're inspired by this idea that by the time, this is a staggering fact, by the time we go through this lifetime, something like 75% of us will be living with parts of our bodies that we were not born with, if we're not already. Okay, all of those cardiac stents and knee replacements and IUDs and that we're all collecting over time are made out of materials like metal and plastic. And we, as bioengineers, many of us in our field had been asking the question, if we're cellular beings and we each started out our lives as being one cell big, why not use the power of cells to generate these replacements instead of using metal and plastic? Okay. You know, I don't want to knock the medical device industry or the pharmaceutical industry, but on the one hand, the medical device industry, medical science has given us better and better simulations of anatomical shape. 3D printing has been really great for this, being able to 3D print metal implants that mimic the shape of the human body. And the cell therapy industry has been very good at creating injectable cell therapies that can help stimulate endogenous repair. But shockingly, we're still replacing parts of our bodies with metal, plastic, ceramic, and so on. And so at EpiBone, our mission is involving trying to do better. You know, this is our mission statement. The most important words are the first three: transforming patient lives through personalized skeletal reconstruction. So here's how we do it. If we can start the video. We start from a CT scan. This is like a three-dimensional X-ray from which we can extract the three-dimensional information and create a personalized puzzle piece shape that matches the defect.
And expanded.
Oh, we can listen.
Within the bioreactor, stem cells are seeded onto the scaffold and given a steady supply of nutrients, warmth, and consistent pressure. This biomimicry encourages the stem cells to differentiate into osteoblasts, which remodel the scaffold into living bone. Once the bone graft is fully formed, it can be implanted into the patient. The graft naturally integrates into the native bone and eventually becomes a part of the patient's own tissue. This process is also being developed for cartilage and osteochondral applications. EpiBone's proprietary method creates new, fully functional tissues without the need for multiple surgeries, graft rejection, or the lack of long-term integration found in current treatments, potentially allowing patients to heal quicker and with an increased quality of life.
So really all we're doing as engineers is, in a bit of a way, we have an identity crisis because the cells are the ones that are doing all the work. We as engineers are making these systems, we call them bioreactors, that mimic the conditions of the human body so that the cells can do what they do best. We call this the biomimetic paradigm, meaning copying nature. Because as what we've learned is, the better that we can copy nature with these technologies that we use to grow cells, the better the cells can do their work.
A CT scan is...
So there are many benefits to this type of approach. Firstly, because we use digital fabrication, we have a perfect puzzle piece shape. Secondly, because it's made from your own cells, there's no risk for rejection. And thirdly, because it's alive, it can continue to remodel and grow, along like with any other piece of your body. Of course, this has to translate into the economics of meaning simpler, faster surgeries, shorter recovery times, fewer complications, and what we hope will be immense cost savings. Because many people think that personalized technologies mean that they should be more expensive, but actually, at scale, they have tremendous capacity to bring down costs. Costs for products themselves, as well as indirect costs to the environment. So I don't want to dwell on EpiBone too long, but I would like to say that we're starting now with bones in the head and face, because that's where shape really matters, where the current treatment options are quite bad, and where the load-bearing requirements are minimal. And from there, we're moving down to treat bones in the rest of the body. And additionally, we're starting now to grow cartilage in conjunction with bones so that we can start to treat joints. And we're starting with joints in the knee. Here's a picture of our clean room in Brooklyn, New York. If anyone's in town, please do look us up and pay us a visit. That's Angela there in the clean room. And I just want to give you a few highlights of what our progress has been over the past 4 years since we've spun out the company. We've successfully implanted 30 pigs and 200 rats. We've built out a 6,000 square foot laboratory in Brooklyn, New York, artisanal bones, we like to say. We've built out a quality team. We've submitted our first regulatory submissions with the FDA in the United States. We've raised $13 million to date. We have an open round of funding if anyone wants to give me any advice about investors we could be speaking to, although this is not a pitch. And we've been partnering with top-tier medical institutions like the Cleveland Clinic and New York Presbyterian. We're starting clinical trials next year. So a lot of people ask, where are we with this? How real is this? And we're at the point now where we're finishing up our animal testing, and we're on the cusp of being able to implant our first patients next year. This is the picture of the dream team as I, open invitation to come and say hello. And I'm really proud of the work that we've been doing, because it's a part of a much larger story in which the future really is being designed by using cells as an elemental unit. We're doing this, and that's what I want to really talk to us about, because this conference is about creativity. And so we're doing this at EpiBone. This is what we're doing. There are others in medicine that are doing similar things. This is Tony Atala's work at Wake Forest University, where they're growing human bladders. There has now been a human living with a tissue-engineered bladder since 2011. This is a picture from Laura Nicholson's company, Humacyte, where she's been engineering vasculature using similar techniques. They're in phase 3 clinical trials and hope to have a product released within the next couple of years. We can also scale down the tissues that we grow in order to be able to study things like cancer. This is an example from Emulate Bio, based in Boston, Massachusetts. Human on a chip technologies allow us to study diseases in a laboratory setting, reducing the need for clinical trials and the need for human testing. But again, this is a creativity conference, and I think learning that cells can be used to transform medicine might not be the craziest idea for many people in this audience. However, I'd like to expose you to some fields in which you might not expect biology to play an impact. Here are some pictures from the MoMA's permanent design collection from 2 different companies. On the left, we have a shirt designed by a company, Modern Meadow, using engineered leather as the black parts of the shirt there. And on the right is a silk dress designed by Stella McCartney, using silk that has been engineered to be produced by yeast that have been transfected with genes that come originally from spider silk, okay? This is from a company called Ecovative. They're based in upstate New York in the United States, and they're using mycelium. They're using mushrooms to generate materials that can be used for everything from furniture to packing materials to lamps. This is Marjolein Helder. She's a Dutch electrical engineer like me, and she's figured out how to harness some of those electrons that are released by plants as part of photosynthesis into the soil, extract them and use them as kind of living batteries. Okay, imagine if power plants of the future are actually made of plants. This is the future that she's trying to make real. This is Ginger Craig Dossier. She's the CEO of a company called Biomason. And I mentioned broken bridges that repair themselves. She's developed a concrete using bacteria, such that when that concrete is cracked and exposed to water during, say, a rainstorm, that rain activates those bacteria, wakes them up, and they self-heal those bricks. Amazing technology. At the other end of the design spectrum, this is from a company called Koeo, where they've been developing these bodysuits that can be used as part of eco-funerals because they remediate the toxic byproducts that are released by the body as part of the decomposition process. There's a very interesting video on the Colbert Report, which is a comedy show in the United States in which their founder, J. Rim Lee, goes to the Funeral Directors Guild and makes a bit of a splash with her bodysuits. And do you see the microbes in here? They're interacting with the ball to destroy the blocks in an example of the world's first biotic video game. Okay, this was developed by Ingmar Rydell-Cruz's lab at Stanford University. And in a module that I was teaching out of the MIT Media Lab, we had students from around the world registering in our biohacking class and developing biotic video games like this, using microbes that they found in pond water in groups as diverse as Peru, Boston, and Switzerland, okay? At EpiBone, I'm constantly inspired by this idea. A woman that I know, Nurit Barshai, is an artist. She's an artist that's now obtaining her PhD in Israel. But she said to me something that's really stuck with me. She said, scientists look for, while artists look at. And she actually has put that to practice. She's a bioartist, and her medium is bacteria. And she's grown beautiful pieces of BioArt. And her work has actually appeared on the cover of the Biodesign book released by the Museum of Modern Art in New York City. And I love this quote by Anton Chekhov. The role of the artist is to ask questions, not answer them. And you know, at EpiBone, our goal is really practical. We want to grow technologies that help alleviate human suffering, extend the human healthy lifetime, practical goals. We look at these images under the microscope, and we are looking for. And I thought, well, if the body really is a work of art, how can we incorporate some of that type of thinking into our work at the lab? And so I just want to show you one example of, so we started an artist residency at EpiBone. We have fun making things like 3D printed jewelry, and in this case, Eliza Stamps, who was residing with us for about 1.5 years, her medium is the pen. She drafts these images. And this image is called 720 Hours. It's an image that took her 720 hours to create, inspired by that cellular image that I showed from our cells growing into bone cells. But it also, incidentally, and not on purpose, corresponds with the amount of time that it takes those cells to differentiate into these bone cells, which I thought was very poetic. So I think, the more that we have technologists work with people in the creative fields, the more likely we are to be able to tackle really difficult issues like bioethics. I also think that biology and science in general is becoming more and more open to folks in the creative fields, which is something that I'm really excited to see. So I just have a moment left. In closing, I hope in this brief time together that I've helped you feel what I feel about how amazing cells are, how they have the capacity to not just transform medicine, but also transform the more creative fields, ranging from things like art and architecture and fashion and funerals, technologies that you wouldn't expect. I also hope to have left you with a little bit of gratitude for the bodies we live in that are made out of cells, and the power that those cells have to create technologies inspired by nature that can help us meet head-on certain global challenges. Because if we can produce energy using biological capacities so much better than we are currently doing using traditional chemistry and physics, we have the capacity to really meet some of these global challenges in our larger ecosystem beyond our bodies and help save the planet. And so I want to leave you with a provocative thought. If the first industrial revolution was about machines, okay, and the second industrial revolution, which you could argue we're in the middle of right now, was about data, is about data, wouldn't it be exciting to think that the third industrial revolution, as biology becomes the new data, could be about life? So, thank you for your time, and thank you for this opportunity.